All right, AP, so I just want to give you a quick, quick practice test that students have had in the past. Obviously, these are not necessarily aligned to AP questions, but I think it should still be helpful. So anyways, last page is the answer key. So go, well, hopefully you've taken the test, because that's what I told you to do. Take the test. If you need to look at how I solve problems because you got them wrong, you might look through the video. So anyways, here we go. Number one, pretty straightforward. I'm not going to write the entire k expression, but just k is going to equal right side over left side. So I've got 2 NH3s, and my NH3 concentration is 0.4. So 0.4 squared over nitrogen, which is 0.2, times hydrogen, which is 0.1. And we're going to cube that, even though it doesn't look like a cube. And I'll pull a calculator up. And there's a calculator. So we're going to have 0.4 squared. So I'm just going to say 0.4 times 0.4 divided by 0.2 divided by 0.1 divided by 0.1 divided by 0.1, and we get 800. And 800, I'm pretty sure, is that answer, right? So that's number one. Number two, given the following reaction, let's get down like that. Given the following reaction and its equilibrium concentration, or equilibrium constant, calculate the numerical value of the equilibrium constant for the following. So kind of if I look at those two equations, to get the bottom equation, I need to reverse it and take the square root of it, because my coefficients are all half of what they are. So I'm taking the square roots and reversing it because it's the opposite direction. So again, I'll get scientific, so I'm going to have 3.6 times 10 to the 8th. I'm going to take the square root of, or I'm going to take the inverse of that. Inverse, and then square root. So that. So 5.2 times 10 to the 5th. 5.2, yep. Okay, so that one's letter D. Alrighty. Number three. So when a system A plus B is in equilibrium with C plus D, what is true? The forward reaction is stopped? No. The reverse reaction is stopped? No. Both of them have stopped? Definitely no. They have the same rate. They're always changing. They're just changing at equal rates. D, neither has stopped, and the sum of concentrations of A, B must be equal, then no. So definitely letter D. Number four, large equilibrium constant results in the addition of a catalyst? No. Indicates the reaction favors the formation of products. That seems to be the correct answer. It's definitely not reactants. Indicates that it has a large rate constant. Not at all. Who cares about little k compared to big K? Or like the rate constants from kinetics compared to equilibrium constants of equilibrium. So definitely letter B. Let's see, number five. Nitrogen oxide and bromine combine to form nitrosyl bromide. So I think we got some math to do on this one. So grab my pen. Let's see. So we've got NOBR, so 1.32 over 5 squared. So again, this is my K equals. And then I can have 0.45 over 5 squared. And lastly, 0.17 over 5. Nothing. All right, so I'll get my calculator out. So I'm going to have 1.32 times 1.32 divided by, what is it, 0.45, divided by 0.45, divided by 0.17, and then my 5s in my denominators that are squared cancel. I've got a 5 in the denominator, so I'm going to end up multiplying by 5, so times 5. So 253, and I'm pretty sure 253 is the answer on 5. Alrighty. So number 6, which of the following statements about the reaction quotient is false? The value of Q can be used to predict equilibrium concentrations. I don't think that's good, but let's keep going. It has the same expression as Kc. That's true, so it's not that one because we want to know which was the false one. Its value is calculated using non-equilibrium concentrations. That's true. If Q is bigger than K, the reaction must move to make more reactants. That's true because Q is bigger than it should be, so we want to make it smaller. That means our denominator needs to get larger, or our numerator needs to get smaller. And then the opposite also has to be true. So if D is true, E has to also be true. So if we go back to A, Q doesn't help us to predict what K values are. K tells us what K values are. All right. Next, which of the following statements is true for a chemical system in a dynamic equilibrium, except for concentrations of reactants and products must be equal. That's not true. Just the rates are equal, but they are not equal. The reaction is endothermic. We need to know more information. It's exothermic. Definitely neither of those. The chemical reaction proceeds in a forward direction until all the reactions are consumed. No, that would not be equilibrium. And then lastly, the concentrations of reactants and products remain constant over time. So it must be E. So the very fact that I can calculate one of these Ks, notice my reactions or my concentrations are constant over time in order to calculate another constant, which is capital K. So E is true. They're constant concentrations because the rates are the same. Their concentrations appear to not be changing. They are changing, but they're changing at the same rate, so they're really remaining constant, which is kind of a little bit out there and a little bit esoteric. All right, number 8. At a certain temperature, Kc is 25, and a reaction vessel contains the following. All right, so really, it doesn't say it's at equilibrium, so I'm going to calculate Q and compare it to K. So I'm going to come back over here. K equal, whoa, that's bad. Control Z that guy. Okay, so I've got HBr, and I'm going to square that, all divided by 0.1, 0.1. So I can tell this answer is going to be 25. We can do the math real quick. So 0.5 times 0.5 divided by 0.1 divided by 0.1. So 25. So because my K and Q equal each other, it means that Q equals K, or the concentrations I currently have happen to already be at equilibrium. Okay? Yeah. So be able to do one of those in the tests. That would be a good question that AP likes to ask where it's not equal to K. I think that's probably still an AP question where for so many years it wasn't equal. Oh, let's throw one in where it is equal, because students won't be expecting that. All right, so number 9, consider the following reaction, which all reactions products are gases. That's fine, that's fine, that's fine. All right, so it looks like this will probably be an ice table type problem. So if I come back over here, I've got 1 mole of A, 2 moles of B, and none and none. After equilibrium has been established, I've got 0.5 moles of D. Right, so I know my X must be 0.5. So that means I'm going to have 1 mole of C, because remember this is plus 2x, and this is plus x, and this is minus 2x and minus x. So I'm going to have 1 of this left, and I'm going to have 0.5 of this left. So it looks like if I have, I don't know, all these things over each other, that's going to be squared, that's going to be squared. My answer is going to be 1. So 9 is 1 on that one. All right, 10 is a great question that people had questions about every year, just about. All right, not many people figured this out on their own. So this might be the only question you look at. All right, so another ice table. I've got 1.07. I've got 0, I've got 0, I've got plus x, I've got plus x, I've got minus x. And this is like that one problem I did on the board a couple weeks ago that was the one with making ammonia, all right? So anyways, it's kind of like that. So the equilibrium pressure in the tube is 1.54 atmospheres. So if I come down here to my equilibrium pressures, I've got 1.07 minus x. I've also got a plus x and a plus x. So what that's saying is the pressure at equilibrium is 1.54. So if I add up all three of my gases, they should sum to 1.54. So what I see is minus x plus x is going to get rid of a set of x's. So I really have 1.07 plus x equals 0.54, which means that x is going to equal 0.47. All right. So if I set up my k expression, I'm going to have 0.47 times 0.47. Remember, 0.47 is my x, so 1.07 minus 0.47 is going to be 0.6. 0.60, and if I do the math on that, 0.47 times 0.47 times 0.47 divided by 0.6, we get 0.368, and I believe D is the answer to number 10. Okay. All right, so come back over here to 11. The numerical value of the equilibrium constant Kc is 0.5 when a reaction. All right, so on this one, I've got K, and K equals 0.5, and that's going to equal my products. So SO3, and that is 10, and I'm squaring that, all over O2, which is 2, really times x squared. All right. So I just want to find out what is the equilibrium concentration of SO2. All right. So I'm going to go ahead and do, let me move my calculator. So I'm going to do 10 squared, 10 times 10 divided by 2. And then if I'm cross multiplying, I'm going to switch my x squared and my 0.5. So I'm also going to divide this by 0.5. I get 100. If I take the square root of that, I get 10. And so my answer would be B on that one. Alrighty. Next, closed system. I guess we'll scroll down a little bit. Yeah, I got plenty of room. All right. So again, you might set up an ice table. You might be able to do this in your head a little bit, but we'll set up an ice table. So I got hydrogen's 1.25. 1.75 is iodine, and I got 0, and then this is going to change minus x, minus 2x. At equilibrium, the partial pressure of hydrogen is 1. So this is 1. So my x must be 0.2 or 0.25. So I'm going to have 1.5 of my iodine, and twice 0.25 is 0.5 of my HI. So I just want to plug those numbers in. So now I'm going to have 0.5 squared on top. So I know it's not C or E. I'm going to have 1 in the denominator and 1.5. So it looks like answer D is the correct answer. Okay. 13. At 450 Celsius, 2 moles each of hydrogen, iodine, and HI are combined in a 1 liter rigid container. The value of Kc is 50, which of the following occurs as the system moves towards equilibrium. All right, so really, on this one, I've got 2 of everything. So I just want to find Q, all right, and compare Q to K. So Q is going to be 2 squared all over 2 times 2. So it's going to be 1. Right? So Q equals 1. So Q is definitely less than K. So if Q wants to become greater, all right, I need more products, less reactants. So it's going to move towards the right side. So more H2 and I2 will form. False. That's going to move towards the left side. More HI will form. That seems to be the right answer. All right. Letter C, the total pressure will decrease. So if so we have 2 moles of each on both sides. The pressure is not going to change, whether it goes left or right. No net reaction will occur. False, because Q doesn't equal K. All right, so it looks like letter B is the correct one on that one. All right, so 14 is a good one. All right, so this is definitely an AP question because the graphics are AP. I'm guessing this is one of those questions that had probably 2 or 3 multiple choice questions related to the question stem at the top. So really, if I look at the top, phosphorus pentachloride is in equilibrium with phosphorus trichloride plus chlorine. All right, so additional chlorine is injected into the system at equilibrium. Which of the following graphs shows the rate of the reverse reaction as a function of time? So chlorine is right here, so that's why it's asking what does the reverse rate look like, because I'm going from right to left. So if I just inject some chlorine in with like a syringe, all right, the pressure of the chlorine, or the concentration of the chlorine, either way, is going to spike immediately. So it's neither A nor C. It's not going to go up gradual. If I inject it, it's going to go up really quickly. All right. So notice B and C both have that just immediate input of concentration or pressure. So the difference in these two things is, notice here, the pressure is lower than we began with. Up here, the pressure once equilibrium is established is higher than we began with. Okay. So conceptually, hopefully this makes sense. It has to end higher than we began with, all right? So if I inject chlorine, some of that chlorine is going to go make PCl5. PCl5, if I make too much of it, it's going to make some of the chlorine back, and we're going to reestablish equilibrium. So if I add chlorine, there's no way the chlorine will end up less than what it started at. It's always going to have a higher concentration or higher pressure than the initial concentration or pressure that it had already established at equilibrium. Okay. Next one. CCO2 decomposes, reaction, temperature. All right, so this is gonna be another one, kind of like that other one we did. So again, I think it's like was it number 10? I don't know, whichever that one was that we did. So if I come over here, I've got what is it? 1, 0, 0. This is going to change minus x plus x plus x. So I've got 1 minus x. I've got plus x plus x. And all of these equal 1.2 ATMs. Okay, so the total pressure at equilibrium is 1.2. So again, one of my x's is going to cancel. I'm left with 1 plus x equals 1.2. Which means x is 0.2, right? So then I'm going to have, what are we solving for, Kp? So I'm going to have 0.2 times 0.2, my two products, all over 0.8. All right. So 0.2 times 0.2 divided by 0.8, so 0.05, and I believe that's letter C, or letter B, all right. 2 more. For which following reaction mixtures would reducing the volume of the container cause the equilibrium to shift towards the products, right? So I want it to go towards the products, and I want to make my box smaller, all right? So letter A, I've got solid on the left, solid gas on the right. So if I make this box smaller, it's going to shift to which side takes up less space. And solid takes up less space than gases, so it's going to shift towards the left. So that will not increase my products. Next one, I've got a solid and 1 mole of gas on the reactant side, 2 moles of gas on the product side. So if I make my box smaller, it's going to shift from 2 moles of gas to 1 mole of gas, or it's going to shift to the left again. C looks like my winner. I've got 2 moles of gas on the left, 1 mole of gas on the right. So if I make my box smaller, it's going to shift to the right-hand side, because 1 mole of gas takes up less space than 2 moles of gas. So C appears to be good. Let's look at D. D is equal moles of gas, so it's not going to shift either way. All right, so letter C. So the last one, 17, the equilibrium constant for the gas phase. What is the value? Okay, so this is just one we're manipulating one to figure out the other one. And we're not even solving it, just what will the equation look like. So if I look at my top one, has an equilibrium constant of 95. So on the bottom, it looks like I'm doubling everything and reversing everything. So I'm going to have the inverse square. So letter D, because I'm inversing it, or taking this reciprocal, and I'm squaring the 95. Okay? So anyways, hopefully that was helpful. If you missed some of these things, hopefully just my explanation made sense. And I'm kind of being there a little bit without being there. All right?